Hello, everyone, and welcome back to the HSMA program after the HSMA summer break. Hope at least some of you managed to have a little bit of time off, bit of relaxation, and are coming back refreshed and ready to carry on with the kind of final third of the training program of this initial phase one. Today we're kicking off with module six. So module six is all about modeling behavioral aspects within our systems, but also looking a little bit at some of the structures within our system, which is what we're going to be focusing on this morning using a technique known as system dynamics. And the kind of modelling that we're going to be talking about both this morning and this afternoon and also next week, quite different to the kind of modelling you've seen so far. So far, really, you've been exposed to discrete event simulation for modelling kind of queuing problems, a bit of geographic modelling, some machine learning, a bit of natural language processing, but now we're getting into a slightly different way of looking at our systems. And again, hopefully the approaches we're showing you here may spark off some ideas for potential projects. Don't forget that you do need to be thinking about your projects and what you're going to be doing. I see people starting to post in the project ideas forum, which is great, and do keep posting their feedback. We've got another project development clinic as well on when I think is it this week? I think it's this week. Or maybe it's next week. I can't remember. But we've got no. I think it's this week. No, it isn't. Anyway, we've got a project development clinic coming up, and do come along to those. They're really useful for getting a bit of feedback, and also useful for us to hear about some of the ideas that you've got for your project work. And there's been some fantastic ideas that come through so far. So hopefully, as you go through this training, you're starting to get some ideas about how this stuff might be applied in various ways for your problems in your organisation. I'd also flag up at this stage. This is probably obviously there's another after this module. There's another two modules. This is probably the final module where we are showing you techniques around which you would probably want to build a project. So module 7 and 8 are mainly focused on useful and important stuff that will help you with your project work. Things like version control and developing web apps and some forecasting work and other sort of analytical approaches. But you probably wouldn't base your entire project around them. They are things that you would add into to your project. So, and we've designed that deliberately so that you've got sort of plenty of time to be thinking about what your projects are going to be. So really, by the end of this module, so by the end of next week, you've kind of been exposed to the various modelling and data science methods that we're going to be showing you. And hopefully one of those, at least, will have sparked off some ideas that you can then pursue for your projects. But back to today, and we're going to be talking about system dynamics today, commonly abbreviated to SD. What is system dynamics? Well, it's basically a kind of modelling approach where we're really interested in the structure of the system itself. And by the structure, we mean the way that the components of that system and the way they relate to each other, and we're looking to capture that structure in a modelling approach. And it's quite a useful approach if you're trying and find out whether there's kind of some inherent problem with just the way in which your system is structured. There's something inherently wrong about the way the system's set up, and because of that approach, it's often known. You may hear it referred to as whole systems modelling as well. It doesn't have to model whole systems, but it commonly does for this very reason that it kind of zooms right out, and you can look at the way in which a system is configured and the way in which all the component parts interact to see if there may be inherent issues. Um, I'm not. I'm going to say right now, I am not the biggest fan of system dynamics. I think there are a lot of bad system dynamics models out there that tell us nothing. However, that is not to say that it is without its merits. And I think a really good use of system dynamics is to try and identify where problems might be that you could then sort of focus in on, and perhaps use other modelling approaches to try and sort. The other great thing about system dynamics, and the way we're going to be teaching it today, if you're not a big fan of Python, you've been struggling with Python, there is no Python, there is no coding whatsoever to build your system dynamics models. We've been using an online framework called Insight Maker. It's completely drag and drop. So those of you that sit to the back teeth of Python for the moment, this is a nice respite for you, and hopefully will allow you to build some really nice models really easily. So that's hopefully a positive. So as we're saying that a fundamental principle of system dynamics is that structure determines behavior. So it's all about the way in which a system is structured. Let's talk a little bit about causal loop diagrams. Now, causal loop diagrams, you've probably, some of you may well have encountered before. Don't worry if you haven't, because we're going to look at them. But for those of you who have, causal loop diagrams are effectively a form of qualitative system dynamics. Basically, a causal loop diagram is a kind of a way of trying to map various influencing factors within a system and the direction of those influences and what we call the polarity of those influences as well. And we'll talk more about that in a second. And causal loop diagrams are quite useful because they allow us to try and identify what are known as feedback loops. That is, we'll talk more about those in a moment as well, but basically the things that are sort of going around and potentially maybe causing problems depending on the context, and may help us understand by picking out where these feedback loops are, why we are seeing certain system level emergent behaviors. And that might help us identify where we might need to focus our efforts if we're trying to improve the system in some way. In a causal loop diagram, we may see things like this. So these are some example influences that show both direction and polarity. So here, what this thing is saying here is that as the number of people who access, the number of people accessing GP services influences the waiting time to see a GP. That makes sense. Okay. So that's what that arrow says, that this thing influences this thing, okay? The plus sign basically means they move in the same direction. So that is to say, for example, as the number of people who access GP services increases, the waiting time to see a GP also increases. Okay, that makes sense. That's fairly straightforward. So we've got the direction, so this thing influences this. And we've got the polarity, which indicates whether they're moving in the same direction or not. And here's an example of one which has a negative polarity. So here we've got the number of people who are admitted to hospital will influence the number of beds that are available in the hospital. But here we've got a negative polarity, which means they move in different directions. So, which makes sense if we think about that. As the number of people who are admitted to hospital increases, the number of beds available decreases. Okay, so they are moving in opposite directions. Now, it's important to note, if you're new to causal loop diagram system dynamics, it's important to just remember, because you can get caught out with this, that plus doesn't mean increase and minus doesn't mean decrease. It means plus means same direction, minus means opposite direction. So it's same and opposite, not increase and decrease, and that can throw you off a little bit if you're a bit new to this. It's probably not the greatest way to note them really, but that's the standard. So we talked about feedback loops a moment ago, and we said that these are kind of the things that we are probably most interested in if we're developing a system dynamics model, because they might indicate where there are potential issues in our system. And there are basically two kinds of feedback loop that you're looking for. The first is known as a reinforcing loop. Probably all of you are familiar in some ways with a reinforcing loop. If you're familiar with the term vicious circle, or indeed virtuous circle, depending on the context, whether it's positive or negative in terms of what it's producing. That is just a vicious circle is just an example of a reinforcing loop. Basically, a reinforcing loop indicates that there is a kind of snowballing effect that is going on, where things are continuing to either increase or decrease because of the particular dynamics within the system. Okay. So here, this is an example of a reinforcing loop. So we've got, as the number of people accessing GP services increases, then the waiting time to see a GP increases. And as that increases, the number of people who are sick increases. And as that increases, the number of people who are accessing GP services increases. So you've got this kind of snowballing effect that more people are accessing GP services, which is increasing the waiting time to see a GP, which is leading to more sick people, which means even more people are accessing GP services, etc. So you kind of got that kind of snowballing effect, and that would work in reverse as well. As that decreases, this will decrease, and that will decrease, etc. And that can help us identify that there might be an issue in that part of the system. And to help you identify whether you've got a reinforcing loop, if we look at the polarity of our influences within the loop, a reinforcing loop will either have an even number of minus signs, or it won't have any at all. So here we haven't got any at all, no minus signs, so we know that this is a reinforcing loop. It also means that if you were to talk through the loop, you'll always reach the same conclusion that you started with once you get back to the start of the loop. What do I mean by that? Well, let's talk this through. So I'm going to say it again. As the number of people accessing GP services increases, so remember that statement, as the number of people accessing GP services increases. As that increases, waiting time to see a GP increases. As that increases, number of sick people increases. As that increases, number of people accessing GP services increases. I've just said exactly the same as I did when I started. Therefore, I've reached the same conclusion, and it is a reinforcing loop. Now, reinforcing loops can become particularly problematic if the thing that is being reinforced is not good. And so, sometimes it's a good thing that you've got a reinforcing loop, but if you don't want the thing that it's producing, then that can indicate a problem. And it can particularly be a problem if you kind of get a bit of spillover from these loops. So if you've got a loop that is causing a bad thing, and then you've got a kind of spill out from that, then that can be even more problematic. So in this highly simplified example, you can imagine that potentially this loop then spills out into the number of people attending ED, which of course makes sense. That we are, as people are struggling to access GP services, more people will turn up to the emergency department. Okay, so that's admittedly a sort of highly simplified version of that kind of system, but that helps us to understand that there is a problem with the structure and the dynamics of this particular system. So that's one type of loop, a reinforcing loop. The other type of feedback loop that we get is known as a balancing loop, and that's basically the opposite. Okay, so a reinforcing loop, basically things snowball, they keep increasing, or decreasing. Whereas a balancing loop basically indicates that the dynamics, the structure of that system is causing these things within the loop to kind of balance themselves out or cancel themselves out. And that might be, again, it might be a good thing, it might be a bad thing, depending on what the thing is, what the loop represents. So here we've got an example of that we've got the number of people admitted to hospital. As that increases, the number of beds available decreases. And as that decreases, remember the plus sign here means same direction, so as that decreases, the capacity to admit patients also decreases. And as the capacity to admit patients decreases, so does the number of people admitted to hospital. If we think about that for a moment, of course that makes sense. It has to be a balancing loop, because otherwise you would just have a hospital with an infinite number of people in it, which obviously can't happen. So hospitals get full, and that's because of this balancing loop. They can't admit more people. Okay, so that's an example of a balancing loop. And a balancing loop, so a reinforcing loop will either have no minus signs for the polarity, or it'll have an even number. A balancing loop will always have an odd number of minus signs, and that will mean that if you talk through that loop, you will reach a contradictory conclusion when you get back to the start. So let's do that here. So remember this first sentence I'm going to say the number of people admitted to hospital as that increases. Okay, as that increases, the number of beds available decreases. They're going in opposite directions. As the number of beds available decreases, capacity to admit patients decreases, same direction. As capacity to admit patients decreases, number of people admitted to hospital decreases, same direction. So I've just said the opposite. I started by saying as the number of people admitted to hospital increases. Once I went around the loop once, I ended up saying as the number of people admitted to hospital decreases. I reached a contradictory conclusion, because it's balanced itself out basically. Okay, so let's consider a very, very simple system just to get our heads around this. Let's consider the system of the chicken and the egg. Okay, so this is, brace yourself, this is going to get complicated here. So we've got chickens, right? And they lay eggs. And eggs hatch into chickens. If we've got more chickens, it means we've got more eggs. And if we've got more eggs, it means we've got more chickens. And so the chicken and egg system I put to you represents a reinforcing loop, at least in this simplified version. There are complicating factors in reality. But let's just imagine there are no other factors. Chicken and egg is a reinforcing loop. As the number of chickens increases, the number of eggs increases, the number of eggs increases, the number of chickens increases. Reinforcing loop. Okay. Before we move on, let's kind of cement what we've covered so far and get you a little bit of hands-on practice with reinforcing loops. But before we do that, Sammy, are there any questions that have arisen in the chat so far?
No, nothing so far.
Great. Okay. Cool. That's hopefully it's a nice, relatively straightforward session this morning to ease you back in. Okay. So what we're going to do, just to practice what we've learned so far, is you're going to go into your groups and you're going to now try to build a causal loop diagram. And I want you to build a diagram that describes the behavioural influences involved in people adhering to social distancing and other preventative measures in the early stages of the COVID-19 pandemic. Now, this is a bit freeform, and there's no sort of right or wrong answer for you. This is just to get you practicing doing some causal loop diagrams. But the way I'd suggest you do this is, so obviously have somebody sharing the screen who's going to be building the diagram with everybody feeding in. You may want to use some collaborative software to do this if you want, but it's not compulsory. And I would start by putting in the centre some preventative measures, so entries that cover preventative measures. So things like the number of people who are wearing masks in required settings, the number of people staying 2 meters away from others, number of people washing their hands for at least 20 seconds, all that kind of stuff. Okay. Then what I want you to do is start thinking about all the factors that you can think of that would directly influence each of those numbers of the things that you've written. It doesn't have to be these 3 things, it could be other things. And which are directly influenced themselves by the number of people that are adhering to these measures. So things that influence these things and things that these things influence. Okay, so think about in both directions. And then for each influence that you identify, I want you to note with a plus or a minus sign the polarity of that influence. So whether they both go in the same direction, as one increases, the other increases, as a plus, or if they go in different directions, as one increases, the other decreases. Then I want you to have a look, as you start to build this up, whether any of those factors that you've written down link with other things that you've written down as well, and whether there are things that you haven't written down. So you gradually start to sort of build out from the middle, identifying factors as you go, and the linkages between those factors. Just gradually keep building that up. As you do so, I want you to be on the lookout for reinforcing loops and balancing loops. And any that you identify, you should make a note of. Okay. And also think about whether that tells you something interesting, or what it is telling you at the very least, and whether that might be interesting or not. Think as well about what insights you're able to draw from this map as you build it up. Think about what the map is telling you, and what this diagram might suggest might be happening. So I'm going to give you about 45 minutes plus a 5-minute break. We're actually running a little bit ahead of schedule, so I might give you a little bit longer. I'll tell you what, we'll come back at 1:45, so 10:45, because that was the time we were going to come back pretty much anyway. So you'll have until 10:45, so use the time however you like. When we come back, we're going to ask a couple groups to just quickly present the diagrams they've come up with, but we're going to ask you all to post your diagrams or link to them within your PSG channels, and Sammy will judge the top 3 and award some points for that. Okay, hopefully that's all clear. We will be floating around and look forward to see what you come up with. So let me stop sharing and we'll open up the breakout groups. Hi everyone, welcome back. I managed to get around, I think, to most of the rooms and saw some really interesting causal loop diagrams actually. So very interested to see what people have come up with. If you haven't already, please make sure you post either a link to it or PDF or the file itself or whatever, however you've done it, in your peer support group channel, so that Sammy can look at them all. But we're just going to ask a couple groups just to very quickly take us through their diagrams now, and of course to do that we are going to use the good old wheel of names to pick a couple groups. So let's spin the wheel and see who is first up. I think it's going to be, Paula. So if somebody from Paula wants to share their screen and talk us through your diagram.
I think someone else is already sharing, or have you stopped?
Oh, I've stopped now, sorry.
Share. Hold on. Screen take. Is that showing up yet?
Yeah, that's come through.
Okay. So we started sort of with the central premise, obviously, about number of COVID infections, and then we talked about the 3 things that were mentioned in the lecture about sort of number of people social distancing, number of people wearing masks, number of vaccinations, and sort of the sort of loops that fit in there. Sorry, my brain's a bit not with it today. A bit lacking sleep. Yeah, so obviously got more COVID infections. If you get more people vaccinated, that will then reduce the number of hospital admissions. You've got, but also if more people are vaccinated, you will get a reduction in the number of COVID infections. God, my brain's just not working today at all. So then we linked into number of COVID infections, number of hospital admissions, which was sort of part of the lecture as well. And the fact that as there's more admissions, number of COVID beds available goes down. We also talked about obviously there's COVID beds and there's non-COVID beds. So you've got to bear that kind of things in mind. So that would be almost like a separate loop, but it might link into this because they might have to turn more non-COVID beds into COVID beds. Obviously, as the number of COVID beds goes down, the capacity to admit patients also goes down, which then has an influence on the number of hospital admissions. We also brought in about the fact that if you get your clinical staff diagnosed with COVID, what's going to happen there? That would then impact the number of hospital admissions because you can't do as many. So then we went off on a bit of a tangent looking at things like impact of social interaction, mental health, and sort of loops there. So less social interaction means increase in mental health conditions, which will then lead to more demand for GP appointments. They'll make more referrals for mental health treatment. That will increase waiting times for mental health treatment. We also looked at some of the sort of social things. So, for example, if more people get vaccinated, then even if COVID infections are going up, people might still choose not to wear masks. So, so you'd think that people would they'd get vaccinated, look at the number of COVID infections, that's still going up, or I'll keep social distancing. But a lot of people will go, I'm vaccinated, I'm okay, I'm not bothered. Same thing again. So people social distancing, if they're vaccinated, they go, I don't need social distance, I'm okay. So that's sort of independent to the number of COVID infections. Then we even got into things like the new variants and the impact that would have. And then we sort of looped off into increased demand for AI to help develop new vaccines. More people want to do HSMA. And then that would increase the number of working COVID vaccines, and it would also increase the demand for Cornish pasties. So
Absolutely, which is the main purpose of HSMA, which is ultimately just a very large smokescreen for my pasty business on the side.
Yeah, well, so then you could get into more people, going down that part of the world for holidays and all kinds of things. But, and that could increase COVID infections down there. So it's all. So a bit of a rambling there, but.
No, not at all. Some really interesting stuff you put out there, and I think, I mean, interestingly, I think when you build up these causal loop diagrams, I think a number of the groups you found this that you start to explore all sorts of things and start to sort of spring to mind. You start to build these things out. They are a bit exploratory, and they're designed to try and help you think things through and draw out whether there's anything interesting you pick out. So
I suppose I guess that's maybe one of the limitations of these, that you start to have to exclude things because they just get too complex.
Yes, and it's probably best to go in with a kind of razor sharp sort of focus on something that a particular aspect of the system you want to look at, or to evolve to that, and sort of split it off. So, yeah, fantastic. Thank you very much. Okay, so we'll spin the wheel once more and see who is next up. Rather than share my screen again, I'll just spin it. You can trust me, and it is going to be. It's ARM. So somebody from ARM, if you want to share your screen, please.
Yes, 1 second. Oh, is everyone able to see that?
Yep, that's come through.
So we kind of took the approach that, Animal Crossing, Nintendo, all these video game spikes happened during COVID, probably had quite an impact on the number of people being infected and all of that. So we were looking at a number of things, so mainly focusing on Animal Crossing and Nintendo. You can see it definitely had an impact on Nintendo. And we'll have a look at our maybe not so complicated diagram, but more colorful, I guess. That's a positive. So we've got a number of infections up here. So that has an increase on Nintendo's profits, as we've seen here. And as Nintendo's profits go up, because people are playing more video games at home, the number of people playing Animal Crossing goes up, which makes them nicer, so they follow the rules. So from here, initially we were kind of thinking mainly this is the loop over here, so they become nicer, and then they follow the rules better, so the number of infections go down, which would then have a sort of negative impact on there, which anyway, but then we kind of thought maybe Nintendo is benefiting from this. The number of infections going down isn't a good thing for Nintendo, so we thought maybe Animal Crossing is designed so that people forget how to cross the roads in real life and end up back in hospital, which increases the number of infections. If you've got more people in hospital, the number of infections will go up, and then that has a separate loop. So we kind of went, I'm not sure if this is a loop that exists, but we're kind of thinking that this could have a positive and negative impact at the same time and how that would work. I'm not sure if it works completely, but that was kind of our thinking. And then we had this coming off here, which is because people are nicer, crime becomes lower, which is just something that goes off separately into a different direction. So yeah, we weren't sure if Nintendo was being like the hero of this story or the villain. So I think that's up to the reader to decide. But yeah, that's all from us. We mainly just
Brilliant.
talking about Nintendo stuff.
Yeah, thank you. Really interesting and entertaining spin on it, and yeah, really, again, sort of an interesting way in which you've found quite an interesting sort of balancing loop and a reinforcing loop, actually, with some of those items in play there. So yeah, very, very interesting. And again, this is the sort of thing that these diagrams can help you think through some of this more unusual stuff that may not have been considered. So to clarify, we're thinking that Animal Crossing saved us all during the pandemic. I think that's what we've concluded there. We've got a nice balancing loop, kept everything stable. Awesome. That's our learning from this morning. Okay, so thank you both for sharing that, and so Sammy will have a look at those and also the remaining 8 as well, and we'll come back to you with some PSG point awards for that. Just to say, from this point going forward, for those of you worried that the leaderboard looks as though it's all over the place, which it absolutely is at the moment after the hackathon before the summer break. From this point forward, we're not just giving the standard sort of 15, 10 and 5 points for first, second and third. Instead, we're going to be identifying the top 3 and awarding ad hoc points based on the quality of what you've done. So there is the potential to get lots and lots of points if you come up with something absolutely amazing. And just depending on that will also vary depending on the scale of the task as well. So we will let you know how those points are awarded later. Okay, so let me share my screen again, and let's go back now to the slide. So we've talked about causal loop diagrams, but which is a form of qualitative system dynamics. Let's now talk about putting numbers into this kind of stuff and talking about quantitative system dynamics. So let's go back to our wonderful chicken and egg system, where we said we've got chickens and eggs as in a kind of reinforcing loop, whereas the number of chickens increases, the number of eggs increase, and the number of eggs increases, that leads to an increasing number of chickens. So far this is a qualitative, there's no numbers attached to this, this is just a kind of causal loop diagram representation of our system. But for this system we could create a quantitative system dynamics model, because we could attach numbers to describe the rate of flow between the elements of our system. And that, when we talk about system dynamics, often we talk about, it can refer to both, but often we talk about quantitative system dynamics and kind of flow rates. So, but what we mean by this is that we can say how many eggs chickens lay per unit of time and how many eggs hatch into chickens per unit of time. Before we do that, though, there's some sort of concepts within quantitative system dynamics that we need to get our heads around, because it can be a little bit odd, some of this. So let's have a look at how we build up a system dynamics model. So here are the kind of the 4 key building blocks of which are known as primitives of a system dynamics model. The first is a stock. So a stock is basically something that holds whatever the stuff is that is flowing around your system. Okay. Now, an easy way to think about a system dynamics model is to think about a kind of plumbing system. It's quite a good analogy for understanding how these things work. So a stock basically holds whatever it is that's sloshing around your system. A stock holds that stuff. So imagine a water tank holding some water. The other big primitive that we have is a flow, and a flow allows whatever it is that we're modeling, the stuff that's sloshing around our system, to move from one stock to another stock, or to move from a stock out of the system, or indeed to move from nothingness into the system, into a stock. And the rate at which this stuff flows we can control a bit like a kind of valve on a pipe controlling the rate of flow of water. And these two primitives are basically the core concepts within a system dynamics model, stock and flow. And you may have heard them described before as stock flow diagrams. This is exactly what they are. Okay, so stock, which holds the stuff that's sloshing around, and the flows transport it from one stock to another, or out of the system, or into the system. But we've also got these extra things here. So we've got these things known as variables. So a variable basically represents something that is not otherwise captured by our model, but which can itself influence either the level of stuff in a stock or the rate of a flow, or maybe even both, but isn't otherwise captured by stocks and flows. And then we have this final thing down here called a link, and a link is basically something that allows us to connect any of these primitives to another to say that this, we can use this thing to determine this thing, but there's no actual flowing takes place. So it's a bit like a flow, but there's no flow. Okay, so as an example, we could use a link to connect a variable to, for example, a flow rate. And then when we determine the flow rate, we can say, well, we can draw from the information in this variable, but it's unlike a flow, nothing is flowing. Okay, there is no stuff flowing from the variable into this flow rate. Stuff only flows along flows, basically. Okay, so a link says I need to use this information from here to here. It's like basically like the influences you were just talking about, saying this will influence this. I need to draw on that information, but it's not a flow. Okay, so let's say that we know that chickens lay on average 5 eggs per week. And we know that fertilized eggs take on average 21 days, 3 weeks to hatch. So in our model, we're going to start with 100 chickens and no eggs. So what came first in our model was indeed the chickens. And we're going to just assume initially, at least, that all of our eggs are fertilized. Okay, so this is a very simplified system where we're just assuming all chickens, all of the eggs that they lay, they're all fertilized and they'll all hatch into chickens, basically. That's not obviously the case. But for the purpose of demonstrating this, it'll suffice. And let's say that we want to track our chicken and egg populations over time. Now, the way in which we're going to do this, if we're going to build this into a quantitative system dynamics model, is going to feel a bit unusual compared to some of the stuff that we've talked about elsewhere in the course. Because there are some quite drastic changes with a system dynamics model compared to something like a discrete event simulation or even an agent-based simulation that you'll see this afternoon. So some of the key differences with a system dynamics model: the entities, the things that are flowing through your model, are not represented as individual entities. So discrete event simulation, you have discrete entities, so things, individual, often patients, but it doesn't have to be. Patients come in and they queue for a system, and then they go through that part of the system, then they go to the next process, etc. And they are all modelled as little individuals, okay, that are in that queue. But in a system dynamics model, that doesn't exist. In a system dynamics model, the thing that's flowing through is a continuous mass of stuff. Okay. Again, think of water flowing through your system. Another key difference is that system dynamics models are not stochastic. So all of the modelling that we've looked at so far is stochastic. It has an element of randomness in there to capture real-world variability. And that's why when we build our discrete event simulations, we run the model multiple times over multiple runs, because we might have a run of good luck, we might have a run of bad luck. It almost represents, sort of lots of different day in the life of our clinic or whatever it may be. But with a system dynamics model, we actually have a deterministic model. There is no variability. Every time you run that model, you'll get exactly the same results. And also, with system dynamics models, particularly because of these kind of these differences here, we're generally interested in kind of looking for general patterns or dynamics, insights that we can draw out from analysing the structure and dynamics of our system, rather than the kind of question that we would ask of a discrete event simulation model, which is things like, you know, how many doctors do we need to meet the demand X% of the time, or what do we predict the impact will be on waiting time if we add in another nurse, or whatever. Those kind of questions. That's not the kind of thing that you could ask of a system dynamics model, but that's not really how they're designed. And part of the reason I don't like system dynamics models is that a lot of them end up just trying to fudge what would be better represented as a discrete event simulation. So it's important to understand there's a distinction here. Discrete event simulation is modelling a queuing problem of individuals flowing through a system, queuing up for things to happen to them, and you're interested in the resourcing and the queuing and the pathway. With a system dynamics model, you're basically exploring the dynamics of that system and how those things interact. You're looking for general patterns and insights. Much as you did with your causal loop diagram a moment ago, you're looking for sort of general insights into that system. You are not going to get out of that system dynamics model, if you built it correctly, sort of things like, okay, well, we're going to need 5 doctors. That's not an output of a well-built system dynamics model. An output is more likely to be, we seem to have a problem over here that this is causing a problematic increase. And then you may then explore and say, well, how do we solve that? You might turn to another modelling method like discrete event simulation to then zoom in on that bit of the system. So let's have a little look at an example of some of these quirks for if we're going to build our chicken and egg model. So we said that eggs on average take 21 days to hatch. And let's imagine we've got our time unit can represent anything we like, but we're going to have it representing weeks, because we know that chickens lay on average 5 eggs per week and they take 21 days to hatch an egg. So let's just make our time unit weeks. How do you think we will describe the number of eggs hatching per week? Well, the answer is possibly not what you might expect. The way in which we describe the number of eggs hatching per week in a system dynamics model is the number of eggs divided by 3. Why is that? Okay, so let's think about this. If we had 1 egg, it would take 3 weeks, 21 days to hatch. But in system dynamics world, so a discrete event simulation, if you were modelling for whatever reason this in a discrete event simulation, you'd effectively have presumably an activity that would hold the egg for 3 weeks, and at the end of the 3 weeks, out would pop a chicken. That's not the case with system dynamics. In system dynamics, if an egg takes 3 weeks to hatch and your time units are weeks, 1/3 of the egg would hatch per week, because it is a continuous mass of stuff. You've got a continuous mass, not a series of discrete entities. So 1/3 of that egg would hatch per time unit. If we had 2 eggs, each week, 1/3 of each of those 2 eggs would hatch, which basically means after week 1, we'd have 2 1/3 of eggs hatched, or if we put that a bit more simply, 2/3 of an egg hatched. Although they are different eggs, in system dynamics world, it's just 2/3 of an egg, because it's continuous mass. It doesn't distinguish that there are different eggs. It is just continuous mass of egg. So we've got 2/3 of an egg hatched. And that kind of makes sense. If we think about it, after 3 weeks, if we had 2 eggs, we'd expect 2 chickens, because it takes 3 weeks for an egg to hatch. We've got 2 eggs. 3 weeks later, we should have 2 chickens. And that, of course, bears out, because that would be, so 3 times 2/3. So we've got 2/3 of an egg hatching per week. After 3 weeks, we'd have 6/3 of egg hatched. In other words, 2 eggs hatched, 2 chickens. So essentially what we're saying is that the number of eggs hatching per week in our system dynamics model is the number of eggs times 1/3, because 1/3 of each egg will hatch per week. which we can then just simplify to the number of eggs divided by 3. It's a bit weird, okay, and that takes a little bit of getting your head around. It is a very different way of thinking. This is exactly why you don't use it to answer the kind of questions you use to answer use a discrete event simulation to answer. So we're going to show how we can build a system dynamics model using this package called Insight Maker, which is, as I say, an online development framework that allows us to build system dynamics models. It also allows for the building of agent-based simulation models. We are not going to be using it for that. When we come on to the agent-based simulation stuff, starting this afternoon and then next week, we're going to actually be using a package called Mesa in Python. I do not believe in framework software other than Mesa's a bit different. It just basically allows you to create a agent-based simulation in Python with a few shortcuts. You don't have to define what an agent is and all that kind of stuff. A lot of agent-based simulation framework software is very limited, and as we'll see this afternoon, the whole point of an agent-based simulation is you can pretty much do anything. So that's why we're not using it, just to flag off. But it is very good for system dynamics. The nice thing is, as I say, it uses a nice drag and drop interface, which allows anyone, regardless of their experience, to be able to put together a system dynamics model very easily. You don't have to install any software. You don't have to have any coding knowledge. You can put together a model and you can share it with anyone you like anywhere in the world, and they can access it and they can run the model and they can play with the model and they can build their own offshoot of that model if they like. So let's have a look at Insight Maker, and we're going to try and build a system dynamics model of our chicken and egg system. So I'm just going to minimize this, and I'm going to go to insightmaker.com here. When you do this, you'll unless you've used it before, you'll probably find this is blank, so it'll look a little bit different. But this has got my previous insights here. But I've already got one that I've stored, but I'm going to create a brand new one. So you should have that button. If you click Create New Insight, it'll actually come up with this sort of getting started instructions and some sort of demo things to show you stuff you can do. You can click that to clear it, but do have a look at it if you're interested yourselves. So the first thing we're going to do is we're going to add 2 stocks to our model. And remember, stocks hold the stuff that is sloshing around our system. So one of the stocks is going to represent the number of chickens that we've got, and one is going to represent the number of eggs that we have. So to add primitives to our system dynamics model, we click the primitive button, the big button on the top left. We click that, and it'll ask us what primitive we want to add. And you can see that in the top, we've got the system dynamics ones of stock, variable, and converter. Don't worry about converters for today. So I'm going to click Add Stock, and then it brings one up, and I can left click and I can drag that wherever I like very easily. And I can also rename it. If I just double click in the stock, I can call that whatever I like. So I'm going to call one chickens, and then I'm going to add another one here, and I'm going to call that eggs. Okay, nice and simple, straightforward so far. Okay, so I'm going to set up my system so that, as we said at the start, I'm going to have 100 chickens at the start of my system and no eggs. Okay, so if we left click on a primitive, a set of options relating to that primitive will come up on the right of the screen. So let me just move this out of the way so I can see it. So if I left click on chickens, a number of options will then appear over here relating to a stock, and specifically the stock chickens. And one of the things I can set here is the initial value. So this is how much stuff there'll be in this stock at the start. So I want 100 chickens. So I'm going to type in 100 here. Also, I don't know why they do this. The allow negatives button will be on by default. That means that you can have a negative number of chickens if your system, I mean, it won't happen in our case, but if we had an advanced version of our model where chickens are dying off, then it would allow it to go down below 0. And that is the default, which is very odd, I find, in system dynamics model. But anyway, you can turn it off just by clicking that. So we can't have less than 0 chickens. The number of eggs that we've got is already, it defaults to having a value of 0 in a stock. So that's fine. So we've got 100 chickens at the start and no eggs, but I'm just going to turn off the negatives because we don't want negative eggs. It won't happen in this anyway, but just to make sure. Okay. Oh, sorry, I have to keep moving this. Right. So now we're going to set up, we've got our 2 stocks. I'm going to set up a flow that flows from eggs into chickens, and that's going to represent chickens that are hatching. Essentially, our eggs become chickens. So again, we're going to look over to the top, but this time we're going to click flows and transitions. And what we're going to do, if I bring down, so you can see next to the primitive button, there are these 2 options here, flows and transitions and links. It defaults to flows and transitions. You can only have 1 active at any one time, so you make sure that one is selected if you want to flow. Just going to move that down slightly. And then all I need to do to create a flow, and if that's selected, is to hover over the center of the thing that I want to connect from, so the center of my egg stock, then until I see this arrow appear, then I left click and I drag up to the thing I want to connect it into, and that will create a flow. Okay, so that's flowed. We've now got a flow from eggs into chickens, which is what we want. That represents eggs hatching. So I have to keep moving this other way. I can also rename this, so I'm going to call it eggs hatching. Sorry, this is really annoying. I'll put it here. Eggs hatching. Little tip, it's quite useful when you're thinking about naming stuff in a system dynamics model. Think about your stocks as being kind of noun based and your flows as being verb based. The flows represent something happening, whereas the stocks represent an amount of something. Okay, so eggs, then we have eggs hatching and they turn into chickens, basically. You can also manipulate these arrows a little bit because I may want things coming back the other way as well. So if I do that, if I click on the flow here, if I left click the circle in the middle and drag it out, I can drag it out here, and that might be quite nice for this particular diagram. It will leave the name by default where it is, or it moves it a little bit offset. If you click on the yellow square, you can drag that wherever you like. So I'm going to put it back in the middle, but you can have it wherever you like. Okay, so that's that. So we've set up the flow rate of eggs into chickens, representing eggs hatching. Now we need to go the other way. We need to specify the rate. Sorry, no. I'm getting ahead of myself. So we've set up the flow rate of eggs into chickens. So eggs hatching. We need to set up the rate of that flow. So at the moment we're saying that there is a flow between eggs and chickens. Okay, but by default, if I left click on that flow, and the options will appear on the right, you can see the flow rate will default to 0. That means that nothing will flow from eggs to chickens, and that a flow rate will always default to 0 when you create a new flow. So nothing will flow by default. So even if we've got, we haven't got any eggs, but if we had 10,000 eggs in here, nothing would flow into chickens unless we change this flow rate. At the moment, the tap on this flow is off. Okay, but we want to change it. So what do we want to change it? We needed to change it to the flow rate that represents the rate at which eggs are hatching, and that represents the number of the amount of stuff that we want to flow from eggs into chickens per time unit. So if our time unit is weeks, that's the number of eggs hatching per week, which, remember, we said in bizarre system dynamics world is eggs divided by 3. Okay, that's the amount of stuff we want to flow from eggs into chickens per week. So if we click on the flow over here, we can set up the flow rate, and if I click in the box, you'll see it'll appear with things that I can refer to, and that will be anything that's connected to it. So this flow is connected to both eggs and chickens, so I can refer to those things if I so wish, and I do. I'm going to click on eggs, and then I can say eggs divided by 3. That's basically the rate of flow. So every time unit in our model, which is going to represent a week, the number of eggs divided by 3 amount of stuff will flow from eggs into chickens. Hope that makes sense. Right. Okay. So I was getting ahead of myself before. So we've got that sorted. We've now captured the fact that eggs are going to hatch at a rate of eggs divided by 3 per week. But we need to sort out the other flow. Okay. So we need to also capture the fact that chickens lay eggs, which we haven't done so far. However, whilst eggs flow into chickens, we can validate that as a valid assumption in our model. We can say, well, an egg effectively becomes a chicken because it hatches. It's not really true that a chicken flows into an egg. Okay, a chicken lays an egg, it doesn't become an egg. Okay, we could argue an egg becomes a chicken. We can't argue a chicken becomes an egg. Okay, what we need to deal with this slightly differently. We can't just have then a flow flowing from chickens into eggs. That doesn't make any sense at all. In fact, what's happening in our model is we need eggs to come into being from nothingness, but the rate at which they come into being from nothingness is partly dependent on the number of chickens, because that will determine how many eggs are getting laid. So to have a flow from nothingness, the way we do this in Insight Maker is that we can drag out a flow from the stock that we want it to come into, out into nothingness, and then reverse that flow. So it then comes back into it instead. So let me show you what I mean. So we want a flow into eggs from nothing. Okay. So I've still got flows and transitions highlighted here. I'm going to highlight the arrow over the middle of eggs. And I'm going to left click and drag into nothingness. Okay, and you see a little cloud appears. However, that's the wrong way around, because we want it to come from nothingness into eggs. So I left click here, sorry, no I don't, I right click, and it'll bring up these little options here, and I can click reverse direction, and now I've got a flow from nothingness into eggs. So from nothing became eggs, and eggs become chickens. Okay, that's starting to make sense in System Dynamics world. I'm also going to rename it from flow to something a bit more useful. So I'm going to call this the laying of eggs. That's what this represents. We also now, of course, need to define the flow rate for this flow. So what is the flow rate for the from nothing into eggs? Well, it's essentially the number of eggs that we want to be laying per week. And that depends on two things. It depends on how many chickens we've got, and it depends on how many eggs each chicken would lay per week, which is our time unit. So we're going to need to link the chicken stock to this flow rate here, because we're going to need to refer to the number of chickens to determine, that's going to partly determine our flow rate. Now we could just hard code that and say, well, chickens lay 5 eggs a week and base it just on that. But we might want to play around with that. So we're going to use a variable instead and link that in. And the variable will basically store the number of eggs that a chicken lays per week. And then we're going to link that up as well as the chickens using our links. So if I click on primitive, this time I'm going to add a variable. I'll drag that over here. And this is going to refer to the number of eggs one chicken lays per week. Okay. And if I click on that, left click on that, I can set a value for that variable. And remember, we said it's 5. A chicken lays 5 eggs a week. So that's number 5. So I could hard code that down here. But this just allows us, if we wanted to play around with that. And we can set up, in fact, little sliders. If you click on that, the user can then play around with the number of eggs a chicken lays per week without messing around with the formulae. So we've got that here. So the laying of eggs is going to depend on the number of chickens we've got, as well as the number of eggs that one chicken lays per week. So I need to link both of those things so I can refer to them in the flow rate. So if I click on links now when I hover over the middle of a stock or a variable and left click, we'll get a link rather than a flow. Remember, a link, nothing flows along. We're just saying I need to be able to refer to this information. So I want to link chickens into this flow rate, and I also want to link this variable into this flow rate. Now, when I click on this flow rate here, and I click in the flow rate box, you can see I can refer to both eggs and chickens. And why hasn't that appeared? Is that not connected? Let me try that again. That should have appeared. There we go. I don't think I connected it properly. Do be careful. You have to. Sometimes it can look as though it's connected, and it hasn't. So make sure it lights up in green when you drop it. So now when I click on that flow rate, you can see I can refer to three things when I define this rate of flow. I can refer to eggs because it's connected to eggs because it's flowing into eggs. That would have before that would have been the only thing that I could refer to. However, I've also now connected chickens using a link, and I've connected my variable that I've created up here into it, so I can refer to those things too. So now I can specify my formula for this flow rate, effectively that's going to be a very simple formula. It's going to be the number of chickens times the number of eggs that each chicken lays per week. That's all the formula is. So if I click in here, I can say chickens multiplied by number of eggs one chicken lays per week. That's how much stuff we want flowing from nothingness into eggs per unit of time in our model. Therefore, if we've got one chicken and it lays 5 eggs, 5 units of stuff will appear in eggs after week 1. I'm also going to turn on, for this variable, I am going to turn on the value slider. And we can set those up. You can set up a minimum value, a maximum value, and what the increment you want to be. And then when you run the model, you can actually then play around with it, as you'll see. Excuse me. You can also, I've talked about these flow rates here. We've just set up some fairly simple formulae. If you click on this little expand box here next to flow rate, you can do all sorts of things, and it includes its own functions that you can write. You can write conditional logic, complex mathematical functions, if you so choose. So there's lots and lots of stuff that you can do. You can store in variables, while loops, all of that sort of stuff. You can do programming-based stuff using its own little language over here as well. I would be cautious about doing anything too complicated unless you've got data to support it, so just be aware of that. But we're just going to keep it nice and simple here. The flow rate is chickens times the number of eggs that a chicken lays. Okay, so I think we've done all of that. Yes, we have. Okay, right, so our model is now ready to go. So we've got chickens and eggs. We've got 100 chickens at the start and no eggs. We've got eggs coming into being from nothingness. The rate at which they come into being is determined by the number of chickens we've got, plus the rate at which, or the number of eggs that one chicken lays in a week. And then eggs flow into chickens. That is the chicken and egg model, chicken and egg system described in a system dynamics model. Now, once you've built the model, you can then get it set up with some extra little options. There's all sorts of things you can do. I'm going to show you a couple little bits that you can do here. So if you click on edit info, sorry, is that right? Is it just... Why is that not... Sorry, bear with me 2 seconds. That should have... They changed this. I think this has changed again. Okay, right. Well, we're going to go into settings for a moment. So if you click on the settings, you can actually set. I mean, it doesn't really matter as long as you know, but it does allow you to specify your own what your timing does represent. So I can select weeks here. I'm going to start at time 0. I'm going to set it up so that it runs for 52 time units, so 52 weeks, or a year, essentially, and it'll increase by 1 time unit per time. Don't worry about these other options. Let me just click apply on that. Oh, is it? I have to click save. Oh, it's here. Sorry, I hadn't clicked Save Insight. So if I click Save Insight, I can name my insight. So I'm going to call it Chickens and Eggs Live. I can give it some optional tags that will allow people to search for this insight. If I say choose, I'm not going to do that for a moment. And I can also put in a description if I want that describes what this is doing. I'm just going to put hello world, just so you can see how that's moving. You can also select whether you want this to be public or private. By default, it will be public, so anybody can search for, run this model, take a copy of it themselves. It is open source by default, which is great. You can choose to make them private if you want. We would encourage you, obviously, to make them public. You may sometimes want to make them private and whilst you're working on it, and then make them public if you so choose. But it's highly unlikely you'd be putting anything that's too confidential on here anyway, but you do have that option. So once I click Save, you can see it's then appeared with the name of the model here, my name as the author, and the description that I wrote down here. So everything there? Yes, that's all set up. Right, so we can now run the model. How might you run the model? Could it be the large button that says Simulate at the top right? Yes, it could be. So if we click Simulate, this will now run the model. Remember, it's a deterministic model. So it'll run the same every single time. And it'll appear with this display here. Now, by default, which is, again, really weird, it displays on this graph absolutely everything you've got in the model. But you probably don't want to track absolutely everything. For example, it seems to make sense that we track the number of chickens and eggs over time. We probably don't want to track the value of this variable, which is just going to remain constant at 5 throughout our model, because that doesn't change. You can have them change, but it's not going to in our model. So you can actually configure that, and you can select which parameters you want to be captured. So I'm going to take out that variable there, click Apply, and that's now removed from the graph. You can also do all sorts of things. There's options. I'll let you explore this, but you can do scatter plots, tables, all sorts of other things. The agent map obviously only applies for agent-based simulations. But we can see from our graph that after 52 weeks, we seem to have an exponential increase in both chickens and eggs, which of course we would expect. We have a system where chickens are just infinitely laying eggs, and eggs are hatching into chickens, and no chickens ever die, and all of the eggs are fertilised. And so, of course, we've got a chicken and egg population explosion as we would expect. But it does appear that our model is functioning as we would expect it to. If I just go into the table, just so you can see the table view of this. You can see it'll track the number of items and all the primitives that you have said that you want to track. In this case, it's my 2 stocks of chickens and eggs over time. So you can see the number of chickens, the number of eggs. We start with 100 chickens and no eggs. After week 1, we've got 100 chickens and 500 eggs, etc., etc. Just to flag this up, because this might look a bit weird, some of this initially. So at the start, we've got 100 chickens, no eggs. That all makes sense. After 1 week, we've still got 100 chickens because we've got no eggs that hatched. But we've now got 500 eggs because each chicken lay 5 eggs within that week. So that makes sense. But then it can look a bit weird. And this is, again, where you have to start thinking in continuous mass of stuff with system dynamics. So after 2 weeks, we will actually have 266.66 recurring chickens. That represents the 100 chickens we had previously, plus 500 divided by 3 new chickens. Because remember, of those 500 eggs, a third of those eggs will hatch within 1 week, because it's eggs over 3. So a third of those have hatched and become chickens. So we've now got 266 chickens. And the eggs, similarly, we've got 833.33 recurring eggs. That's the 500 eggs we had previously, plus another 500 that would have been laid in that second week, minus the 500 divided by 3 eggs that have flowed from eggs into chickens. In other words, those that have hatched. Told you system dynamics is weird, but this is how it works. Okay, so continuous mass of stuff is what you need to be thinking about. You can also explore other people's models as well. So if you go to Insight Maker Home, you can search. If you click on the Explore Insights, it comes up with some popular tags here. Remember, there will be agent-based models here too, but you can search for anything you like. So I don't know. I'm going to put emergency department. Let's see what comes up, and search on that. And we should have. There we go. Now remember, most people will leave their models public by default. They might be just playing around much as we are with the chickens and eggs. That's our colleague Tom. How weird. I didn't realise his model was on there. Tom Monks, there you go. That'll be it. I was just about to say there'll be some really bad models on there. Mind you, Tom hates system dynamics, so I don't know if I can vouch for this, but Tom is an excellent modeler and an excellent academic, so that might be worth looking at. But you can explore what other people have done. And in fact, there's all sorts of nice features that you can explore. You can create little storyboards within this software. It's really nice if you want to kind of create some visual stuff to show people how your system works. But I'll let you explore that at your leisure. So we've overrun slightly, so apologies for that. What I'm going to ask you to do now is to go back into your groups, and you've got up until lunch to design and build a system dynamics model of your choosing. Your model can represent anything you like. If you need a bit of inspiration, have a look at the Explore Insights feature. Don't worry about chucking in accurate data, just make some stuff up, just make some numbers up that seem sort of sensible. I want you to think about how you're going to structure your model in terms of the stocks and the flows and variables and any interface elements that you might want to put in, sliders, etc. Feel free to have a look at stuff we haven't covered this morning as well. And once you've built your model, try running it, explore different parameters, see what insights you can generate. Now, we're not going to have time for people to present that, but if you post links to your models, which you can do, let me show you. If I go back to the chickens and eggs. So as long as this is set up to be public, you can share this simply by clicking the link and basically selecting pasting that into your Slack channel. So make sure it is public though, otherwise we won't be able to see them, obviously. And Sammy's going to decide what her favourite 3 models are and award some points accordingly. Okay, Sammy, any questions that have arisen through the weird world of system dynamics?
So I think the main one that's come out is again around about how system dynamics compares to some of the other techniques that we cover on the course. So, if we're looking for a general pattern or dynamics within the system, what's the advantage of system dynamics? The comparisons that were asked were with things like process mining, other kinds of simulation modeling, feature selection. I'll chime in on process mining. I would say process mining is very good for seeing the how a system is structured right now, or kind of looking directly at process logs to find how a system is working, how the what's it set up like, and is it matching what you think it should be like, etc. It's not necessarily so good for understanding or kind of running a model to see how it's going to look in the future, the actual impact of the system being set up as it is. It could maybe feed into a system dynamics model in some way. Dan, I don't know if you want to add anything on simulation and anything else.
Yeah, I mean, so as ever with these kinds of questions, you should view system dynamics basically as another tool in your tool belt that will allow you to tackle problems. As you probably tell, I'm not the biggest fan of system dynamics. Generally, I think most of you will be looking at problems that are. You need to think about what the questions are. A question that you're asking of a model should always determine how you approach that. In reality, what happens is people tend to be system dynamics people, and so they'll turn everything into system dynamics problems. So you could create pretty much anything in a system dynamics model, the same you could fudge anything into a discrete event simulation model. But just because you can do something doesn't mean you should. And really you should let the question drive. So if your question is primarily about, where are the delays in my pathway, or what would happen if we changed this pathway in this way, or what would happen if we added in more resources or took resources away from this pathway, that kind of thing. Discrete event simulation is your friend for that, and that's what you should absolutely be doing. But if you're sort of zooming out a bit more and just saying, do you know what, is there something inherently wrong with the way in which our system is structured? Is there something about the dynamics of the system as a whole that are potentially causing issues? System dynamics allows you to explore that. It doesn't often give you the solution, though, unlike a discrete event simulation. So it may allow you to say, yeah, well, of course we've got a problem over here, because no wonder, just to take the simplified example from earlier, no wonder so many people are turning up at the ED, because nobody can get a GP appointment, okay? But that doesn't give you the answer. If that was your problem, you were discovering that via system dynamics, you would probably say, okay, so what do we need to do to solve that? How can we improve availability in the GP clinics? And that would probably involve a discrete event simulation, for example. So it's kind of, I would view system dynamics more as a way of kind of exploring your problem and trying to understand where you might need to target your efforts. That's probably how I would use it, more than trying to answer it. But again, it depends what your question is. And indeed, your question might be trying to understand your system and your, there are very many complex systems within health and social care, and I'm sure in policing as well, where you may want to just get a handle on that system and how it all sort of interconnects first. And in which case, probably system dynamics can be a useful tool. There are other tools, as process mining, and just process mapping in itself can be a useful tool. But yeah, it's just another tool in your armory, basically.
Thank you. And the only other one to ask is just, it's going back to the sort of stocks and that kind of the rates around that. So someone just wanted to clarify with the chicken and egg example, if you do have 3 eggs after 1 week, do you have 1 chicken, so 3 times 1/3, and anything around that?
Okay, so if you've got 3 eggs, I'm not quite sure. So if you've got 3 eggs, and then what you're saying, that the following week, will you have 1 chicken? Is that right?
Yes.
Yes.
Yeah, that's.
Yes.
Yes.
Yes. Because you'd have it would be eggs over 3. So if you had 3 eggs, the following week, eggs within that week, eggs over 3 chickens would come into being, and that would be 3 over 3, which would be 1. So yes, it's really weird. It's really weird. And again, that gives you the clue that you are not looking for. Okay, where's the delay in our clinic? What happens if we add in an extra receptionist? This is not the modelling method for you. You can do that using this, and there are the extra features within Insight Maker that allow you to put in things like distributions and stuff. It's not really designed for that kind of thing. You end up with really what you're trying to do is get a feel for your system with a system dynamics model, and it's more about that, because you're ending up with continuous massive stuff. You're looking at these sort of emergent dynamics that very often across very large scale systems, and trying to work out how things interconnect. Don't worry, I promise that the HFA simulation this afternoon is much more interesting than this. There are a few reasons why I keep this system dynamics in. I have seen in HSMA before some people that have come up with some really decent models, actually. Some people will critique, but my job is to say what it is good and isn't good for. I'm not the biggest fan of this modelling approach. So if you're sat there thinking this is a bit weird and a bit fuzzy, and yeah, you're right, it is.
And just to add as well, someone has pointed out as well that this could because of the eggs. Some of obviously a lot of the eggs that are hatching will be male chickens, so no more laying chickens. But that's just in this case, I think, just a simplification of this model, and start to build that in with time. But yeah, that does add a possible layer of confusion here.
Yeah, yes, apologies, sorry. There are a number of simplifications. I'm not suggesting for a moment that we have a secret population explosion of chickens and eggs. This is a highly simplified system. Indeed, previous to this year, the traditional exercise that you would have now done was an accidental chicken massacre simulator, where you had to build in foxes and chickens dying off from natural causes and also from the foxes, and basically had to tune the model to see how quickly you could wipe out the chickens based on the birth rate of foxes, which was kind of entertaining. But I grew bored of that for a while. But yes, indeed, that's what we used to do here. But now, I mean, if you want to do that, go for it. You can build on this model if you so choose for exercise 2, but you can also build something else as well. Okay.
That's it.
Fantastic, thank you. So apologies, we did overrun there, but have a play really for the next 45 minutes. We won't come back before lunch, so I'll leave the breakout rooms open until about 1:20, so you can, if you want to, you can carry on over lunch and play around with System Dynamics if you so choose. But do make sure you do take a break. We'll be floating around for the next 45 minutes anyway, and then we'll kick off at 1:30 with the agent-based simulation proper modelling that I do like. So, apologies if anyone does like System Dynamics. You proved me wrong. That's your challenge. Show me a good System Dynamics model. Okay, right. So I'll put you into your groups now. Have some fun playing around with System Dynamics.